Tonight, we're going to explore something that sounds simple but will fundamentally change how you see the universe. A light year. You've heard this term countless times. Astronomers throw it around casually when talking about space. But here's what nobody tells you. When you actually grasp what a light year represents, when you truly understand the distance it describes, something breaks in your brain. Not in a bad way. In a profound way. Because a light year isn't just a big number. It's a distance so incomprehensibly vast that it challenges everything your mind knows about space and time. It forces you to confront scales that human brains simply weren't designed to handle. And by the end of tonight, you're going to feel that break happen. You're going to see the universe differently, forever. Before we dive in, if you enjoy these deep explorations of space and our cosmic reality, a quick like or subscribe really helps the channel grow. It's a small gesture for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that seems simple. Light. You flip a switch, and light appears instantly. You open your eyes, and you see the world immediately. Light seems instantaneous. It seems like it has no speed at all. It's just there the moment you need it. But light does have a speed, and that speed, while incredibly fast, is finite. Understanding this speed, truly grasping what it means, is the first step in understanding light years. Because a light year is nothing more than the distance light travels in 1 year at its constant, unchanging speed. Light travels at approximately 300,000 kilometers per second. Let me say that again because this number is crucial. 300,000 kilometers every single second. That's about 186,000 miles per second if you prefer imperial units. This isn't an approximation or a rough estimate. Scientists have measured this speed with extraordinary precision. The exact value is 299,792.458 kilometers per second. But for our purposes, 300,000 kilometers per second captures the essence. Let me help you visualize this speed, because numbers alone don't convey the reality. In 1 second, light travels far enough to circle the Earth's equator about 7.5 times. Think about that. The Earth is about 40,075 kilometers around at the equator. That's a massive distance from a human perspective. Early explorers took years to sail around the world. Ferdinand Magellan's expedition from 1519 to 1522 took 3 years to circumnavigate the globe. His fleet of 5 ships left Spain in September 1519 with 270 men. Only one ship, the Victoria, returned in September 1522 with just 18 survivors. Magellan himself died in the Philippines in 1521, killed in a battle with indigenous warriors. The journey was brutal, marked by starvation, disease, and mutiny, and it took 3 years to go around the world once. In the time it takes you to snap your fingers, about 1/10 of a second, light travels 30,000 kilometers. That's about 3/4 of the way around the Earth. In the time it takes to blink your eye, about 300 milliseconds, light travels 90,000 kilometers. That's more than twice around the Earth's equator. In the time it takes you to say the word light, about 1/4 of a second, light travels 75,000 kilometers. That's almost twice around the planet. In 1 second, light could travel from New York to Los Angeles and back about 37 times. The distance from New York to Los Angeles is about 4,500 kilometers as the crow flies. People fly this route constantly. It's about a 5-hour flight. You board a plane at JFK or LaGuardia. You sit for 5 hours watching movies, eating airline food, reading, maybe working on your laptop, and you land at LAX. It feels like a real journey across a continent. You cross multiple time zones. You see the landscape change beneath you, from the cities of the East Coast to the farmland of the Midwest, to the Rocky Mountains, to the deserts of the Southwest, to finally the Pacific coast. Light makes this trip 37 times in 1 second. While you're snapping your fingers, light has crossed the United States 74 times. Let's compare light to things that we consider fast in everyday life. A commercial jet aircraft flies at about 900 kilometers per hour. That's about 250 meters per second. This feels incredibly fast when you're sitting in the plane. You feel it accelerate down the runway, pushing you back in your seat. You feel it climb into the sky, your ears popping from the pressure change. You look out the window and watch the ground rush away beneath you. Cars become tiny. Buildings shrink to the size of toys. You're traveling faster than most people will ever travel in their lives. You're going nearly 3 times the speed of sound relative to the ground. Though subsonic aircraft fly below the speed of sound, light travels more than 1 million times faster than that jet. More than 1 million times. If the jet is traveling at 250 meters per second, light is traveling at 300 million meters per second. The ratio is so extreme, it's hard to comprehend. It's like comparing a snail to a supersonic aircraft. The fastest car ever built, the Thrust SSC, reached about 1,228 kilometers per hour in 1997 when it broke the sound barrier on land. That's about 341 meters per second. Light travels about 880,000 times faster than that car. Even humanity's fastest land vehicle, pushing the absolute limits of what's possible with jet engines and aerodynamics, travels at less than 1/100,000th of 1% of the speed of light. Nothing in nature on Earth comes even remotely close to light speed. Nothing in our evolutionary history prepared us to understand speeds like this. We evolved to understand running, throwing, the speed of a river's current, the speed of the wind. These are speeds of tens of kilometers per hour at most. 300,000 kilometers per second is so far beyond our experience that our brains have no framework for understanding it. Even our fastest spacecraft can't come close to light speed. The Parker Solar Probe, launched by NASA in August 2018, reaches speeds of about 192 kilometers per second at perihelion, its closest approach to the Sun. It uses the Sun's gravity to slingshot itself to higher and higher speeds with each orbit, a technique called a gravity assist. With each pass, it goes faster and gets closer to the Sun. It's traveling faster than any human-made object has ever traveled. It's an incredible achievement of engineering and physics, representing decades of planning and billions of dollars in investment. And yet, the Parker Solar Probe travels at only about 0.064% of the speed of light. It's moving incredibly fast by human standards. At 192 kilometers per second, it could travel from New York to Los Angeles in about 23 seconds. It could circle the Earth in about 3 minutes and 29 seconds. It's moving at about 690,000 kilometers per hour. That's staggeringly fast. But compared to light, it's crawling. Light is more than 1,500 times faster. If the Parker Solar Probe were racing light across the solar system, light would arrive at Jupiter while the probe was still passing Venus. Light would reach Neptune while the probe was still near Saturn. The gap is enormous, unbridgeable with current technology. This comparison helps us understand something fundamental. Light speed isn't just fast, it's fast in a completely different category. It's so fast that it exists in a realm beyond normal human experience, beyond anything we encounter in daily life, beyond anything we've built, beyond anything in nature on Earth. We evolved to understand speeds of running, of throwing spears, of riding horses, maybe speeds of a few tens of kilometers per hour. We didn't evolve to comprehend 300,000 kilometers per second. Our brains simply don't have the wiring for it. Now, here's something that might surprise you. When you flip on a light switch in your room, the light doesn't actually appear instantly. It takes time to travel from the bulb to your eyes. That time is about 10 billionths of a second for a typical room, That's 0.000000001 seconds, or 1 times 10 to the negative 8 seconds in scientific notation. This duration is so short that there's absolutely no way for your brain to perceive it. The fastest nerve signals in your body travel at about 120 meters per second. The time it takes for the signal to travel from your eye to your brain is much longer than the time it takes light to cross the room. As far as your senses are concerned, the light appears instantly. Your perception system simply isn't fast enough to detect the delay. This time delay becomes noticeable, becomes real, becomes important when we start talking about larger distances. And this is where things start to get interesting. This is where we begin to feel the edges of light speed's limitations. Look up at the moon on a clear night, that pale disk hanging in the sky, that familiar companion that's been with humanity since before we were human, since before we were primates, since before mammals dominated Earth. The moon has been there for over 4 billion years, formed likely from debris after a Mars-sized object collided with the early Earth. When you see the moon, you're not seeing it as it is right now in this exact moment. You're seeing it as it was about 1.3 seconds ago. The moon is about 384,400 kilometers away from Earth on average. The distance varies because the moon's orbit is slightly elliptical, ranging from about 356,500 kilometers at perigee to 406,700 kilometers at apogee, but on average, it's 384,400 kilometers away. Light has to travel that distance to reach your eyes, and even though light is incredibly fast, even though it's traveling at 300,000 kilometers per second, it still needs about 1.3 seconds to cross the gap between the moon and Earth. More precisely, it takes about 1.28 seconds, but we round to 1.3. This means there's a delay. When you look at the moon, you're looking into the past, not the distant past, just 1.3 seconds into the past, but it's real. The light you're seeing right now left the moon's surface 1.3 seconds ago. If something happened on the moon right now, if a large meteor struck it and created a bright flash, if it suddenly changed color somehow, if it somehow disappeared, you wouldn't know for 1.3 seconds. You'd keep seeing the moon as it was, not as it is, for that brief moment. Reality and your perception of reality would be out of sync. This had practical implications during the Apollo missions. From July 1969, when Apollo 11 first landed on the moon, through December 1972, when Apollo 17 made the last landing, astronauts walked on the lunar surface and communicated with Mission Control in Houston. There was a communication delay built into every conversation. Every word Neil Armstrong spoke on the moon's surface on July 20th. 1969 took 1.3 seconds to reach Earth. When he said, "That's one small step for man, one giant leap for mankind," those words didn't arrive instantly. They traveled as radio waves, which move at the speed of light, taking 1.3 seconds to cross the void between the moon and Earth. Every response from Mission Control took 1.3 seconds to reach the moon. This created a nearly 3-second gap in every exchange. If Mission Control asked a question, there was 1.3 seconds of travel time for the question to reach the moon, however long it took the astronaut to think and respond. Then another 1.3 seconds for the response to come back. Minimum delay between question and answer was about 2.6 seconds, and usually longer because the astronaut needed time to think and speak. If you listen to recordings from the Apollo missions, you can hear this delay. There's always this pause, this lag. It's subtle, but it's always there. The conversations have an unusual rhythm because of the time it takes for radio signals to cross the Earth-Moon distance, and radio signals travel at the speed of light. Even at light speed, even at the fastest speed possible in the universe, there's a noticeable delay over a distance as small as the Earth-Moon gap. Now, let's go farther. Let's talk about the Sun. The Sun is about 150 million kilometers from Earth. We call this distance one astronomical unit, or AU. It's the baseline we use for measuring distances within our solar system. Everything else is described in relation to this distance. Venus at its closest is about 0.3 AU from Earth. Mars at its closest is about 0.5 AU. Jupiter is about 5.2 AU from the Sun. Saturn is about 9.5 AU. Neptune, the most distant planet, is about 30 AU from the Sun. These numbers mean something because we understand what 1 AU represents. It's the distance from Earth to our star, the distance across which all the light and heat that makes life possible must travel. But what does 150 million kilometers actually mean? How long does it take light to travel this distance? About 8 minutes and 20 seconds. More precisely, it's about 8 minutes and 19 seconds, but we usually round to 8 minutes and 20 seconds, or sometimes just say about 8 minutes. When you look at the Sun in the sky, when you feel its warmth on your face, when you see its light illuminating the world around you, you're experiencing the Sun as it was 8 minutes and 20 seconds ago. The photons entering your eyes right now, the photons warming your skin, left the Sun's surface over 8 minutes ago. They've been traveling through the vacuum of space at 300,000 kilometers per second for all that time, and they're only just now reaching you. This has a strange implication. If something happened to the Sun right now in this exact moment, if it suddenly changed color, if it dimmed, if it somehow exploded, we wouldn't know for over 8 minutes. The event would happen. The Sun would change. But the light carrying information about that change would still be traveling toward us. We'd keep seeing the Sun as it was, not as it is, for 8 minutes and 20 seconds. We'd be living in the past. We'd be seeing a ghost. We'd be completely unaware that reality had changed. Our entire understanding of the Sun's status would be at least 8 minutes and 20 seconds out of date, and there would be nothing we could do about it. No technology, no matter how advanced, could give us information faster than light. The speed of light is absolute. Scientists actually worry about this for studying the Sun. When solar flares occur, they release enormous amounts of radiation. Some of this radiation, particularly X-rays and extreme ultraviolet light, can damage satellites and harm astronauts. We have spacecraft watching the Sun constantly, looking for signs of solar flares. But even with these warning systems, even with spacecraft positioned between Earth and the Sun, we only get about 8 minutes of warning. The spacecraft sees the flare, sends a signal at light speed, and we receive it 8 minutes later. By then, the harmful radiation is already arriving at Earth. For very large solar storms, those 8 minutes might be enough to take protective measures. Satellites can be put into safe mode. Astronauts on the International Space Station can move to shielded areas. Power grids on Earth can be partially shut down to prevent damage. But 8 minutes isn't much time. And we can never get more than 8 minutes because that's how long light takes to travel from the Sun to Earth. It's a fundamental limit. Think about what this means for our perception of the universe. We never see anything as it actually is right now. We always see everything as it was. The delay is so short for nearby objects that it doesn't matter. When you look at a person standing across the room, you're seeing them as they were a few billionths of a second ago. When you look at a mountain on the horizon, you're seeing it as it was a few millionths of a second ago. These delays are so tiny that the distinction between past and present is meaningless. For all practical purposes, you're seeing things as they are now. But when we look at astronomical objects, when we look up and out into space, the delays become significant. They become real. They become something we must account for and understand. The moon is the past. The Sun is the past. And as we look farther and farther out, we look deeper and deeper into the past. Distance and time become inseparably linked. To look far away is to look long ago. This isn't science fiction. This isn't some weird theoretical concept. This is simply what happens when light has a finite speed and has to travel enormous distances. This is the universe we actually live in. Now, here's a question that might be bothering you. Why does light have a speed at all? Why isn't it instantaneous? Why can't information just appear everywhere it needs to be without taking time to travel? The answer comes from understanding what light actually is. Light is electromagnetic radiation. It's a disturbance in the electromagnetic field, a wave that propagates through space. More precisely, it's an oscillation of electric and magnetic fields perpendicular to each other and to the direction of travel. The electric field creates the magnetic field, and the magnetic field creates the electric field, in a self-sustaining cycle that allows the wave to propagate. This speed is the same everywhere in the universe. Whether you're on Earth, on Mars, in another galaxy, or at the edge of the observable universe, light always travels at the same speed. Whether you're moving toward the light source or away from it, whether you're stationary or moving at high speed, light always moves at 300,000 kilometers per second relative to you. This is one of the most counterintuitive facts in physics, but it's been confirmed by countless experiments. Here's something else that's crucial to understand. The speed of light isn't just the speed that light happens to travel at. It's a cosmic speed limit. Nothing can travel faster than light. Not spaceships, not particles, not information, nothing. This is absolute. This is not negotiable. This is a fundamental law of nature. This isn't a technological limitation that we might overcome with better engineering. This isn't like the sound barrier, which people once thought was impassable, but which we broke with better aircraft design. This is fundamentally different. The universe doesn't allow faster than light travel. It's not that we haven't figured out how to do it yet. It's that it's impossible. The laws of physics forbid it at the deepest level. Why? Because of how mass, energy, space, and time are related according to Einstein's theory of relativity. As you accelerate an object, as you make it go faster and faster, strange things start to happen. These aren't just theoretical predictions, they're observed facts, confirmed by countless experiments over the past century. Time slows down for that object relative to stationary observers. This is called time dilation. If you put an atomic clock on a fast-moving spacecraft and compare it to an identical clock that stayed on Earth, the moving clock would run slower. This has been measured directly with atomic clocks on aircraft. It's not a small effect. At speeds close to light speed, time can slow by huge factors. The object's mass effectively increases, or more precisely, its inertia increases. It becomes harder and harder to accelerate further. You need more and more energy to produce the same change in velocity. The amount of energy required to keep accelerating increases without limit as you approach the speed of light. The energy requirement goes to infinity as you get closer and closer to light speed. To actually reach the speed of light would require infinite energy. The universe doesn't contain infinite energy. Energy is finite, bounded. Therefore, nothing with mass can reach light speed. The mathematics is clear. The physics is unambiguous. Light speed is unreachable for anything with mass. Only things with no rest mass, like photons, particles of light, can travel at light speed. And they must always travel at light speed. They can't slow down or speed up. From the moment they're created to the moment they're absorbed, photons travel at exactly 300,000 kilometers per second. No faster, no slower. This is simply what photons do. It's their nature, their defining characteristic. A photon that isn't moving at light speed isn't a photon. Let me tell you about Ole Rømer, a Danish astronomer who lived in the 1600s. He made one of the most important discoveries in the history of science, and he did it by carefully watching Jupiter's moons. In 1676, Roma was working at the Royal Observatory in Paris under the direction of Giovanni Cassini. He was timing the eclipses of Io, one of Jupiter's 4 large moons discovered by Galileo in 1610. Io orbits Jupiter every 1.77 days, periodically disappearing behind the planet and then reappearing on the other side. These eclipses are predictable and regular. Roma was trying to create accurate tables that would predict when each eclipse would occur. Accurate predictions were important for navigation, as they could be used to determine longitude at sea. But Roma noticed something strange. When Earth was closest to Jupiter in its orbit, the eclipses happened earlier than predicted. When Earth was farthest from Jupiter, the eclipses happened later than predicted. The difference was about 22 minutes across Earth's orbit. This was far more than could be explained by measurement errors. Something systematic was happening. Roma puzzled over this. Were the eclipses actually happening at irregular times? Was something wrong with the orbital mechanics of Io? Was Jupiter's gravity somehow variable? No, none of these explanations made sense. The pattern was too regular. The delay correlated perfectly with Earth's position in its orbit. Then Roma had a brilliant insight. The eclipses weren't actually happening at different times. They were happening on schedule, like clockwork. But the light showing us the eclipses was taking different amounts of time to reach Earth depending on how far away Jupiter was. When Earth was closer to Jupiter, the light had less distance to travel, so we saw the eclipses earlier. When Earth was farther from Jupiter, the light had more distance to travel, so we saw the eclipses later. The delay was caused by the finite speed of light. This was revolutionary. It proved that light has a finite speed. It travels. It takes time. Light is not instantaneous. Roma presented his findings to the French Academy of Sciences in 1676. He calculated approximately how long it took light to cross the diameter of Earth's orbit. His calculation wasn't quite right because he didn't know the exact size of Earth's orbit. The astronomical unit wasn't accurately measured yet, but he proved the principle. Light has a finite speed, and that speed can be measured by astronomical observations. This was revolutionary. For thousands of years, people had assumed light traveled instantly. Aristotle, the great Greek philosopher, believed light was instantaneous. He thought vision worked by light rays emanating from the eyes to objects, and this happened instantly. Hero of Alexandria in the 1st century CE argued that light must travel infinitely fast because you see distant stars the moment you open your eyes. Galileo Galilei tried to measure light's speed in 1638. He and an assistant stood on distant hilltops at night with lanterns. Galileo would uncover his lantern, and the assistant was instructed to uncover his lantern as soon as he saw Galileo's light. Galileo tried to measure the delay, but the distances were far too short. At most, they were separated by a few kilometers. At light speed, the round-trip time would be a few tens of microseconds, far too short for human reaction times. Galileo concluded that either light traveled infinitely fast or its speed was too fast to measure by this method. René Descartes, the French philosopher and mathematician, believed light was instantaneous. In fact, he based part of his philosophy on this assumption. He argued that if light had a finite speed, we might notice delays when looking at the stars, and since we don't notice such delays, at least he thought we didn't, light must be instantaneous. Most scientists through the 1600s believed light was instantaneous or at least immeasurably fast. Roma proved them wrong. Light has a speed, and that speed, while very fast, is finite and measurable. In 1676, Christiaan Huygens, a Dutch mathematician and astronomer, used Roma's observations to calculate the speed of light at about 220,000 kilometers per second. This was lower than the true value because the size of Earth's orbit wasn't accurately known at the time, but it was remarkably close given the available measurements. Over the next few centuries, scientists refined the measurement. In 1849, Hippolyte Fizeau in France measured light speed using a rotating toothed wheel. He shined light through the gap between teeth. It reflected off a mirror 8 kilometers away and came back. By rotating the wheel at different speeds, he could arrange for the returning light to either pass through the next gap or be blocked by a tooth. This allowed him to calculate light's speed. He got 215,000 kilometers per second, closer to the true value. In 1862, Léon Foucault, also in France, used rotating mirrors instead of a toothed wheel. He got an even better value of about 298,000 kilometers per second, very close to the true value. In the 1870s and 1880s, Albert Michelson in the United States conducted increasingly precise experiments. He was obsessed with measuring light speed accurately. He built elaborate experimental apparatus with precisely machined rotating mirrors and carefully measured distances. By 1879, he had measured light speed to within 0.02% of the true value. He continued refining his measurements for decades. In 1926, he measured light speed in a vacuum using a precisely surveyed mountain path in California. His value was 299,798 kilometers per second, extremely close to the modern value. Today, we've measured the speed of light with extraordinary precision using lasers, atomic clocks, and sophisticated equipment. We've confirmed that it's constant, that it doesn't change depending on how fast you're moving, where you are, or the direction of travel. And we've discovered that this speed is woven into the very fabric of space-time. It's not just the speed that light happens to travel at. It's a fundamental property of the universe. In fact, as of 1983, the meter itself is defined in terms of the speed of light. The International System of Units now defines the speed of light as exactly 299,792,458 meters per second. This is exact by definition, with no uncertainty. We use this to define what a meter is, rather than the other way around. The speed of light is that fundamental to physics. So when we talk about a light year, we're talking about the distance that light, traveling at this cosmic speed limit, covers in one Earth year. We're talking about a distance that's defined by one of the most fundamental constants in physics. We're talking about a distance that's going to challenge everything you think you understand about scale. Understanding that light has a speed, a finite speed, is the foundation of everything that follows. It's why distances in space become time delays. It's why we see the past when we look up. It's why a light year makes sense as a unit of measurement. And it's why the universe is structured the way it is, with fundamental limits on how fast information can travel, on how quickly we can reach distant places, on how we experience the cosmos. The speed of light is not just fast, it's the speed of causality. It's the speed at which cause and effect propagate through the universe. Nothing can cause something to happen faster than light can travel between cause and effect. It's the maximum speed at which information can travel. And once you understand this, once you truly grasp what it means, you're ready to understand what a light year really represents. Now we're going to build up to a light year step by step, because if we jump straight to 9.46 trillion kilometers, your brain will see it as just another big number and move on. The number won't mean anything. It'll be abstract, disconnected from reality. We need to feel the scale building. We need to watch as distances that seem vast become tiny compared to what comes next. We need to climb this ladder of scale one rung at a time. Let's start small. Let's start with 1 light second, 300,000 kilometers. The distance light travels in 1 single second. That's about the distance from Earth to the Moon and 3/4 of the way back. Remember, the Moon is 384,400 kilometers away on average. Light travels to the Moon in about 1.28 seconds. In 1 second, light covers 300,000 kilometers, which takes it to the Moon with 84,400 kilometers left to travel. So 1 light second is the distance to the moon minus 84,000 kilometers. Or you can think of it as light travels to the moon and then about 78% of the way back to Earth, all in 1 second. Now let's scale up. 1 light minute is 60 light seconds. That's 18 million kilometers. Think about that. 18 million kilometers. The sun is about 8.3 light minutes away, which is where that 8-minute and 20-second delay comes from. 8.3 light minutes equals about 150 million kilometers, which is 1 astronomical unit. So 1 light minute is roughly 12% of the distance from Earth to the sun. 1 light hour is 60 light minutes. That's about 1,080 million kilometers. Over 1 billion kilometers. This number is already getting hard to grasp. A billion is 1,000 million. It's a number we use casually, but do we really understand it? A billion seconds is 32 years. Saturn, the ringed giant, the 6th planet from the Sun, sits about 1.2 light hours from Earth at its closest approach, and Saturn is about 1.2 light hours away. When the Cassini spacecraft orbited Saturn from June 2004 to September 2017, taking spectacular close-up photographs of the planet, its rings, and its moons like Titan and Enceladus, there was over an hour of delay between when it took a picture and when that picture reached Earth. The spacecraft would capture an image, convert it to digital data, and transmit it as a radio signal. That signal would travel at light speed for over an hour before arriving at receiving stations on Earth. 1 light day is 24 light hours. About 25,900 million kilometers. We're now talking about roughly 26 billion kilometers. To write this out fully, 26,000 million kilometers, or 26 billion kilometers. Either way, it's a number that's losing connection to anything we can visualize. Voyager 1, launched September 5th, 1977, is currently the most distant human-made object from Earth. As of 2025, it's about 163 astronomical units from Earth, which is about 24,400 million kilometers, or about 0.91 light days. Let's call it about 22 light hours to be precise. Voyager 1 has been traveling for nearly 48 years. It's been moving through space continuously since 1977. It was launched before personal computers were common, before the internet, before mobile phones. It's been traveling since Jimmy Carter was president of the United States. An entire generation has been born, grown up, and reached middle age while Voyager 1 has been traveling. And it's not quite 1 light day away. 1 light week is 7 light days, about 181 billion kilometers. We're now in a region where nothing human-made has ever been, and nothing will be for decades or centuries to come. This is deep space, far beyond the planets, far beyond the heliopause, far beyond anything we've directly explored with spacecraft. 1 light month is roughly 30 light days, about 778 billion kilometers. We're approaching 1 trillion kilometers now. 778 billion is more than 3/4 of the way to 1 trillion. We're entering the realm of truly cosmic distances. At this distance, if you looked back at the sun through a telescope, you'd see it as just another star. Its apparent magnitude would be about 0, similar to Vega or Arcturus as seen from Earth. It would no longer be the dominant object in the sky. It would be one star among many, no longer clearly special. The solar system, with all its planets and moons and asteroids and comets, would be barely visible even with good telescopes. Jupiter might be visible as a faint dot, but you'd need to know exactly where to look. The inner planets would be completely lost in the sun's glare. Earth would be utterly invisible, far too small and faint to see at this distance. Everything we think of as the solar system, all the worlds humans have observed and studied, All the places our spacecraft have visited, all the planets and moons we've photographed, would be compressed into a tiny region around an ordinary star. The entire solar system, extending out to Neptune at about 30 AU, would span an angular width of about 40 arcseconds as seen from one light month away. That's less than 1/50th of a degree. It would fit easily within the field of view of a telescope, but you'd need that telescope to see anything at all. And now, finally, we're ready. 1 light year is 365 light days, it's 12 light months, it's 52 light weeks. It's 8,760 light hours. It's 525,600 light minutes. It's 31,536,000 light seconds. Watch how quickly the numbers scale up. We started with 1 light second, which was already an enormous distance by human standards, about the distance from Earth to the Moon and most of the way back. And we've been multiplying by larger and larger numbers. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week, roughly 30 days in a month, 12 months in a year. Each step, the distance multiplies. Each step, we move into a larger realm of scale, and we're just now getting to 1 light year. Let's calculate what a light year actually is in kilometers. We know light travels at 300,000 kilometers per second, 24 hours in a day, and 365 days in a year. Actually, more precisely, there are 365.25 days in a year, which is why we have leap years, but we'll use 365 for simplicity. So we multiply 300,000 times 60 times 60 times 24 times 365. Let's do this step by step so you can follow along. 300,000 times 60 is 18 million. That's how many kilometers light travels in 1 minute. 18 million times 60 is 1,080,000,000. That's how many kilometers in 1 light hour. 1,080,000,000 times 24 is 25,920,000,000. That's how many kilometers in 1 light day. 25,920,000,000 times 365. This is where the number gets truly enormous. The result is 9,460,730,472,580.8 kilometers. But we usually just say 9.46 trillion kilometers. That's close enough for most purposes, and it's much easier to say 9.46 trillion kilometers. That's what a light year is. Not a measure of time, despite the word year in the name, but a measure of distance. The distance that light, the fastest thing in the universe, travels in 1 Earth year. Now, before we can truly grasp what 9.46 trillion kilometers means, we absolutely must talk about what a trillion actually is. Because most people have no intuitive sense of this number. We throw around words like million, billion, and trillion in everyday conversation without understanding what they mean. We hear about government budgets in the trillions of dollars. We hear about billionaires. We hear about millions of people. These numbers all sound big, so we treat them as roughly equivalent in our minds. It's a big number is where our understanding stops. But they're not equivalent, not even close. The differences between them are so vast that they exist in completely different categories of magnitude. Let me show you exactly what I mean. Let's start with a million. A million is 1,000 thousands, one followed by 6 zeros, 1 million. If you saved $1 every single day, starting today and continuing without ever stopping, never missing a day, never spending any of it, you'd have $1 million in about 2,740 years. That's a long time. That's longer than any empire has lasted. That's longer than most religions have existed. But it's conceivable. You can imagine a timeline stretching back 2,740 years. That takes you back to about 700 BCE. That's ancient Greece before the classical period. That's the founding of Rome. which according to legend happened in 753 BCE. That's ancient China during the Zhou dynasty. That's before Buddha, before Confucius, before Socrates. Humans in 700 BCE were already civilized, living in cities, writing books, creating art and philosophy. It's ancient, but it's within human history. 1,000,000 seconds is about 11.5 days. More precisely, it's 11 days, 13 hours, 46 minutes, and 40 seconds, less than 2 weeks. You can imagine a period of 11.5 days. That's a good vacation. That's the time between paychecks for some people. It's a comprehensible span of time. You've experienced periods of 11.5 days. You can count every second if you really wanted to, though it would be tedious beyond belief and you'd need to give up sleeping. If you stacked 1,000,000 $1 bills, the stack would be about 109 meters tall. A dollar bill is about 0.109 millimeters thick. 1,000,000 of them would be 109,000 millimeters, which is 109 meters. That's about as tall as a 30-story building. It's the height of Big Ben in London. It's about the same height as the Statue of Liberty from ground to torch. Big, impressive, but comprehensible. You've probably seen buildings that tall. You can imagine looking up at a 109-meter tall stack of money. Now, a billion. A billion is 1,000 millions. We've jumped up by a factor of 1,000. A billion is 1 followed by 9 zeros. This is where things start to change. This is where numbers start to escape normal human experience. If you saved $1 every second, not every day, but every single second, you'd need about 32 years to save $1 billion. 31 years, 8 months, and about 15 days, to be more precise. That's more than the time it takes for a generation to grow up. That's longer than many people's entire careers. That's a significant portion of a human lifespan. If you started counting seconds when you were born and counted continuously without sleeping, eating, or taking any breaks whatsoever, never stopping, never resting, counting one number per second forever, you'd be 32 years old when you reached 1 billion. Think about that journey. From newborn baby to adult in your 30s, and you'd just be reaching 1 billion. Think about that. 1,000,000 seconds is about 11.5 days. 1 billion seconds is 32 years. The jump from million to billion is absolutely enormous. It's not just 1,000 times bigger. It feels fundamentally different. 11.5 days is something you can experience directly, something you've lived through many times. 32 years is a significant portion of a human life. It's longer than many people's entire careers. It's the time from birth to established adulthood, from knowing nothing to being a fully formed adult person with a career and possibly a family. 1 billion grains of rice laid end to end would stretch about 5,000 kilometers. That's farther than the width of the continental United States, which is about 4,500 kilometers. You couldn't walk alongside this line. You couldn't see the whole thing. You'd need to drive for days or fly for hours. Your billion grains of rice would stretch from Los Angeles to New York and then some, or from London to eastern Iraq, or from Tokyo to western India. Now we need to make another jump, from billion to trillion. A trillion is 1,000 billions, 1 followed by 12 zeros. And here's where numbers start to completely lose their connection to anything we can relate to. Here's where scale breaks our brains. If you counted to 1 trillion, counting one number per second without stopping, without sleeping, without eating, without resting, just counting continuously forever at one number per second, it would take you about 31,700 years. Let me put that in perspective. That's longer than all of recorded human history. That's longer than civilization has existed. That's longer than agriculture has existed. Agriculture, the foundation of civilization, was only invented about 10,000 to 12,000 years ago in the Fertile Crescent of the Middle East. Before that, all humans everywhere lived as hunter-gatherers. We moved from place to place following animal herds and seasonal plants. We lived in small, nomadic bands. We had no permanent settlements. The entire human population of Earth was maybe a few million people at most, scattered across Africa, Asia, Europe, and eventually the Americas. Writing systems, the ability to record information permanently, appeared about 5,000 to 5,500 years ago in ancient Sumer in Mesopotamia. The earliest writing we've found dates to about 3,200 BCE. It was cuneiform, wedge-shaped marks pressed into clay tablets using a reed stylus. These earliest texts recorded transactions, business dealings, quantities of grain and livestock. Writing was invented for accounting, for keeping track of who owned what and who owed whom. The pyramids of Egypt were built about 4,600 years ago, around 2600 BCE. The Great Pyramid of Giza, the largest, was built for the pharaoh Khufu around 2580 BCE. It took about 20 years to build, employed tens of thousands of workers, and required sophisticated mathematics and engineering. It was the tallest human-made structure for over 3,800 years. The wheel, one of humanity's most important inventions, was probably invented about 5,500 years ago, around 3500 BCE. The earliest wheels we've found are from Mesopotamia and date to about this time. Before the wheel, everything had to be carried or dragged. The wheel revolutionized transport, trade, and eventually warfare. Bronze working, the mixing of copper and tin to create a harder metal suitable for tools and weapons, began about 5,000 years ago, around 3000 BCE. This transition from stone tools to bronze tools was so significant that we call it the Bronze Age. It marked the beginning of true metallurgy. The first cities, permanent settlements with thousands of inhabitants, appeared around 6,000 years ago. Uruk in Mesopotamia, one of the earliest cities, reached a population of about 40,000 to 80,000 people around 3000 BCE. Before cities, humans lived in small villages at most, usually just extended family groups. To count to 1 trillion seconds, you'd need to have started counting before any of that happened. You'd need to have started 31,700 years ago. You'd need to have started when humans still lived in small, tribal groups scattered across the continents. When there were no cities, no nations, no written language, no agriculture, no permanent settlements, no domesticated animals, except possibly dogs. When there was no metal working beyond perhaps cold hammering native copper. When the wheel didn't exist, when every tool was made of stone or wood or bone, you'd need to have been counting through the entire span of human civilization, through every invention, every discovery, every empire that rose and fell, through the Sumerians, the Egyptians, the Babylonians, the Assyrians, the Persians, the Greeks, the Romans, through the rise of Christianity, Islam, and Buddhism, through the Middle Ages, the Renaissance, the Age of Exploration, the Industrial Revolution, the modern world, through every war, every peace, every triumph and tragedy in human history, through the invention of writing, mathematics, science, medicine, through every book ever written, through every work of art ever created, through every song ever sung, and you'd still be counting today, and you'd still have thousands of years to go before you reached 1 trillion. Let me try to make this even more concrete, even more visceral. 31,700 years ago, modern humans were living in the last ice age. This was the Upper Paleolithic period, during what's called the last glacial maximum. Ice sheets covered Canada, much of northern Europe, and parts of Asia. Sea levels were about 120 meters lower than today because so much water was locked up in glaciers. Britain was connected to mainland Europe. You could walk from France to England. Asia and North America were connected by a land bridge across what's now the Bering Strait. This was about 29,700 BCE. Neanderthals had gone extinct just a few thousand years earlier, around 30,000 BCE. Humans were using sophisticated stone tools. We had learned to make composite tools with multiple parts. We were hunting with spears and atlats, spear throwers that increased leverage and power. We were making elaborate cave paintings on the walls of caves in places like Lascaux in France and Altamira in Spain, though these specific caves weren't painted until later. We were hunting woolly mammoths, woolly rhinoceroses, cave bears, cave lions, giant ground sloths, and other megafauna that have since gone extinct. The world was colder. Much of Earth was covered in grassland and tundra. Forests were restricted to the warmer regions. Humans had barely begun to spread across the globe. We'd left Africa perhaps 60,000 to 70,000 years ago. We'd spread to Europe and Asia. We'd reached Australia maybe 50,000 years ago. But North and South America wouldn't be populated until about 15,000 years ago, when humans finally crossed the land bridge from Asia. There was no complex language as we know it today. We probably had language, but it would have been much simpler than modern languages. Vocabulary would have been smaller. Grammar would have been less complex. We could communicate, but not with the sophistication of modern humans. There was no art beyond simple cave paintings and carved figurines. The famous Venus figurines, small statuettes of women with exaggerated features, were being made around this time. But there was no written language, no permanent records, no history beyond oral tradition passed down through generations. There was no technology beyond chipped stone tools and wooden implements. We knew how to make fire, which humans had mastered perhaps 400,000 years ago. We could make spears and knives and scrapers from carefully knapped flint. We could make clothes from animal hides sewn together with bone needles and sinew thread. But that was the extent of our technology. That's how far back 1 trillion seconds takes you. That's the world you'd need to be living in when you started counting, if you wanted to reach 1 trillion by today. 1 trillion grains of rice laid end to end would stretch about 5 million kilometers. That's more than 13 times the distance from Earth to the Moon. You could wrap your line of rice around the Earth 125 times. You could stretch it from Earth to the Moon and back 3 times with some left over. And a light year is 9.46 trillion kilometers. Every single one of those kilometers is a real distance. It's not an abstract unit. It's not a mathematical concept. It's an actual... The distance you could walk in about 10 to 12 minutes at a normal pace. The distance from the center of one city block to the center of the next in a typical urban grid. The distance of a pleasant walk to a nearby store. A real, concrete, comprehensible distance. And there are 9.46 trillion of those individual kilometers in 1 light year. 9.46 trillion separate, distinct, kilometer-long segments, each one the length of a walk to your local store, each one real, each one counting, each one having to be traversed to cover the distance of 1 light year. When we say a light year is 9.46 trillion kilometers, we're talking about a distance that absolutely dwarfs anything in our daily experience, a distance that towers over anything in human history. A distance so vast that our brains have no framework for understanding it. You can write it down. You can calculate with it. You can use it in equations. But grasping it intuitively, feeling it in your bones, understanding it in your gut, is nearly impossible. Our brains simply didn't evolve to handle numbers this large. We evolved to count the number of people in our tribe. Maybe 20, 30, 50 people. We could count the number of animals in a herd. Dozens, maybe a few hundred if we really concentrated and had a good memory. We could count the number of days until the seasons change. A few hundred days at most, 1 year, maybe a few years if we were keeping track of cycles. We can count to a few thousand if we really try, maybe 10,000 if we're exceptionally patient and dedicated and have a reason to do so. But 9.46 trillion? That's so far beyond our cognitive capabilities that it might as well be infinity. 9.46 trillion is 31 million times larger than anything our ancestors needed to count. The human brain didn't evolve to comprehend numbers this large. We evolved on the African savanna, where the largest number we needed to understand was maybe a few hundred, counting the herd of antelope, counting the rival tribe, counting the days until the migration. 9.46 trillion is not just bigger than these numbers. It's in a completely different universe of magnitude. So let's try to visualize this in different ways. Let's build mental models that might help us grasp the scale, even if we can't fully internalize it. Imagine you had to place markers, one every kilometer, along the distance of 1 light year. How long would it take? If you could place one marker every second, working 24 hours a day without stopping, without sleeping, without eating, without resting, just placing markers constantly at 1 per second, it would take you 300 million years. 300 million years. Dinosaurs first appeared about 230 million years ago. You'd have to start placing markers before dinosaurs even existed, during the Permian period when the supercontinent Pangaea was forming. You'd place markers through the age of dinosaurs, through their extinction 66 million years ago, through the rise of mammals, through the evolution of primates, through the appearance of humans, through all of human history. And you'd still be placing markers today, and you'd have tens of millions of years more to go. Here's another way. If the distance from Earth to the Sun, 1 astronomical unit, 150 million kilometers, were represented by 1 centimeter, then 1 light year would be about 633 meters. That's about 6 city blocks. That's a distance you could walk in about 7 or 8 minutes. This scale makes the solar system very small, shrinking Earth's orbit to the size of a penny, but at least it makes a light year something you can walk in less than 10 minutes. If the sun were the size of a period at the end of a sentence, about 0.5 millimeter across, a tiny dot, then Earth would be an invisible speck about 5 centimeters away. You couldn't see Earth with the naked eye at this scale. It would be about 10 micrometers across, smaller than a human cell. Jupiter would be about 50 micrometers across, still too small to see, sitting about 26 centimeters away. Pluto would be about 2 micrometers across, sitting about 2 meters away. And the nearest star, Proxima Centauri at 4.24 light years, would be another 0.5 millimeter period sitting about 11 kilometers away. That's the distance across a small city. You'd need to drive for about 10 minutes at city speeds to get from one period to the other. That's how much empty space exists between stars, even on this extreme scale where the sun is a barely visible dot. Or think of it this way. If you could somehow shrink space so that 1 light year became 1 meter, just 3 feet, then the observable universe would be about 93 billion meters across. That's 93 million kilometers. That's about 62% of the distance from Earth to the Sun. Even in a scale where a light year, that incomprehensibly vast distance, shrinks down to 1 meter, something you could reach out and touch, the universe is still so large it would stretch more than halfway from Earth to the Sun. The universe is vast beyond any comprehension, no matter what scale we use. These visualizations help, but they all fail in the same fundamental way. They're still trying to make the incomprehensible comprehensible. They're still trying to take a number that's too large for human brains, a number that breaks our cognitive abilities, and squeeze it into something we can grasp. And ultimately, they can't fully succeed. They can't bridge the gap between 9.46 trillion and anything in human experience. Because 9.46 trillion kilometers is simply beyond our cognitive capacity to truly, deeply, intuitively understand at a gut level. But here's what we can understand. We can understand that this distance is real, that it exists, that it's not just a mathematical abstraction. That light actually travels this far in 1 year, moving at 300,000 kilometers per second for 365 days straight. That there are stars and galaxies separated by these distances, and by distances thousands and millions and billions of times larger. We can understand it intellectually, even if we can't grasp it intuitively. We can work with it mathematically. We can calculate with it. We can measure cosmic distances using it. And that understanding, that intellectual comprehension without full intuitive grasp is enough. It has to be. Because it's the best our brains can do. We're not built for this. We're not designed for cosmic scales. But we can still understand them in the way that matters. We can use them to map the universe, to understand our place in it, to measure the vast distances between stars and galaxies. The light year is the distance light travels in 1 year, 9.46 trillion kilometers, a number so large that counting to it would take longer than human civilization has existed, a distance so vast that traveling it at our fastest spacecraft speed would take longer than recorded human history, a scale that breaks our brains because we simply weren't built to comprehend it. And yet, this is the fundamental unit we use to measure the cosmos. Because when you're dealing with the universe, when you're measuring distances between stars and galaxies, nothing smaller makes sense. Kilometers are too small. They result in numbers that are absurdly large and completely meaningless. Even astronomical units are too small for measuring distances beyond our solar system. Light years are the smallest unit that works for cosmic scales. And even light years are too small for the largest distances. For those, we use kiloparsecs, megaparsecs, even gigaparsecs, but light years are where we start. Light years are the foundation. And as we're about to see, when we start actually applying light years to real distances in space, when we start measuring how far away things actually are, the numbers only get more mind-bending from here. Because 1 light year is just the beginning. The universe is measured in billions of light years, and every single one of those billions is 9.46 trillion kilometers. Now, let's put light years to work. Let's measure some actual distances in the cosmos and see what they tell us about the universe we live in. Because understanding the numbers is one thing. Applying them to real objects, real places, real distances is another. This is where the scale truly starts to break our brains. Let's start our journey with our nearest stellar neighbor, Proxima Centauri. This small red dwarf star sits about 4.24 light years away from our solar system. That's about 40,140 billion kilometers, 40 with 12 zeros after it, 40,000 billion kilometers. Proxima Centauri is part of the Alpha Centauri system, which is actually a triple star system. Alpha Centauri A and Alpha Centauri B are 2 sun-like stars orbiting each other. They're similar in size and brightness to our Sun. Alpha Centauri A is slightly larger and brighter, about 1.1 solar masses. Alpha Centauri B is slightly smaller, about 0.9 solar masses. They orbit each other every 79.9 years, sometimes getting as close as 11 astronomical units and sometimes separating to as much as 36 astronomical units. Proxima Centauri is much smaller than either of them. It's about 1/8 the Sun's mass and 1/7 its diameter. It's a red dwarf, the most common type of star in the galaxy. Red dwarfs make up about 70% of all stars in the Milky Way, but they're all so dim that you can't see any of them with the naked eye. Proxima Centauri is so faint that even though it's our nearest stellar neighbor, closer than any other star, you need a telescope to see it. Its apparent magnitude is about 11, far too faint for naked eye visibility. 4.24 light-years. The fastest spacecraft humans have ever built is the Parker Solar Probe, reaching 192 kilometers per second at perihelion. If you could maintain that speed and aim it at Proxima Centauri, it would arrive in about 6,800 years. 6,800 years. Think about what that means. The Sumerians invented writing about 5,200 years ago, around 3200 BCE. The Egyptian pyramids were built about 4,600 years ago. You could have launched your spacecraft when the pyramids were being built, when Egypt was at the height of its old kingdom power, when pharaohs ruled as god-kings and thousands of workers hauled massive limestone blocks to create monuments to immortality. Your spacecraft would still be traveling today. It would still be thousands of years away from arrival. Every empire that has risen and fallen since the pyramids were built, every war that has been fought, every discovery that has been made, every book that has been written, all of it has happened in less time than it would take to reach the nearest star at our fastest speed. The Roman Empire rose and fell. Christianity and Islam were founded and spread. The Renaissance, the Age of Exploration, the Industrial Revolution, the modern world, all of human progress from ancient Egypt to today. And your spacecraft would still be in transit, but there are proposals for going faster. The Breakthrough Starshot Initiative, announced in April 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes a radically different approach to interstellar travel. Instead of building a large spacecraft with chemical or even nuclear propulsion, they want to build tiny spacecraft, essentially computer chips with cameras weighing maybe 1 gram, about the weight of a paperclip, attached to ultra-thin light sails made of reflective material perhaps only a few hundred atoms thick. The sail would be about 4 meters across, about the size of a small room, but incredibly thin and light. It would reflect light almost perfectly. Then, from Earth, they'd fire massive arrays of ground-based lasers at these sails. The proposal calls for a laser array with a total power of about 100 gigawatts. That's roughly the output of 100 nuclear power plants, all focused into a laser beam a few kilometers wide. The laser light would push on the sail, and because the spacecraft is so incredibly light, weighing only a gram or so, it can be accelerated to tremendous speeds. The laws of physics say that force equals mass times acceleration. If you have a small mass and a large force, you get a large acceleration. The proposal aims for reaching about 20% of light speed, which is about 60,000 kilometers per second. 20% of light speed. That's 1/5 of the fastest speed possible in the universe. At this speed, you could travel from Earth to the Moon in 6 seconds. You could reach Mars at its closest approach in about a minute. You could cross the entire solar system from the Sun to Neptune in about 8 hours. It's almost incomprehensibly fast by human standards. At 20% of light speed, these tiny probes could reach Proxima Centauri in about 21 years. Add another 4.24 years for signals to travel back to Earth at light speed, and you could potentially get data from Proxima Centauri in about 25 years from launch. That's within a human lifetime. You could be 25 years old when the mission launches and 50 years old when the data comes back. You could work on the project, see it launch, watch and wait during your prime adult years, and potentially see the results before you retire. But the engineering challenges are staggering, perhaps insurmountable, with anything resembling current or near-future technology. First, you need those incredibly powerful lasers, 100 gigawatts of laser power. That's more laser power than exists on Earth right now by many orders of magnitude. The most powerful continuous laser in existence is only about a few megawatts. You'd need to increase that by a factor of about 30,000. You'd need to build a completely new infrastructure, perhaps an array of thousands of smaller lasers working in perfect synchronization, And this laser beam would need to track the tiny spacecraft as it accelerates away from Earth. The spacecraft would be moving faster and faster, and the beam would need to stay locked on, keeping the light precisely focused on the 4-meter sail. Any deviation, any wobble, any imprecision, and the sail would drift out of the beam. The acceleration would stop. The spacecraft would coast at whatever speed it had reached, which might be only a fraction of the target velocity. Second, the spacecraft needs to survive the journey. At 20% of light speed, you're moving at 60,000 kilometers per second. At this speed, collisions with even tiny particles become catastrophic. A speck of interstellar dust, something far smaller than a grain of sand, perhaps just a few micrometers across, hitting the spacecraft at 60,000 kilometers per second would release energy equivalent to a bomb. The kinetic energy is 1/2 mass times velocity squared. Even a tiny mass at such a high velocity squared releases enormous energy. The spacecraft would need shielding to protect the delicate electronics. But any shielding adds weight, and weight is the enemy when you're trying to accelerate something with light pressure. The more massive the spacecraft, the more energy you need to accelerate it, and the relationship is linear. Double the mass, double the energy needed. If your spacecraft weighs 10 grams instead of 1 gram, you need 10 times as much laser power. The entire concept only works if the spacecraft is incredibly light. Third, you need to communicate with the spacecraft over 4.24 light years. The tiny probe would need a laser or radio transmitter powerful enough to send data back to Earth from that distance. At 4.24 light years, any signal spreads out enormously. The signal strength decreases with the square of the distance. At 4.24 light years, which is about 40 trillion kilometers, a signal is incredibly faint by the time it reaches Earth. You'd need very large receiving antennas on Earth to pick up the signal, and you'd need a powerful transmitter on the spacecraft, which means power, which means weight, which brings us back to the fundamental problem of keeping the spacecraft light enough to accelerate with lasers. It's a vicious cycle of constraints. Fourth, and perhaps most difficult, you need to actually hit Proxima Centauri's star system and fly past it at the right distance and angle to get useful data. Space is vast. Stars are tiny targets. Proxima Centauri is a red dwarf, only about 1/7 the Sun's diameter. That's about 200,000 kilometers across. From 4.24 light years away, you're trying to hit a target 200,000 kilometers wide. That sounds large, but remember, you're approaching from trillions of kilometers away. It's like trying to hit a target the size of a marble from 1,000 kilometers away. Any tiny error in your trajectory, any slight miscalculation, and you miss completely. You fly through empty space, see nothing, and continue into the void. And you can't correct course. At 20% of light speed, you're moving so fast that any course correction would require enormous amounts of energy. Energy you don't have in a 1-gram spacecraft. So you get one shot, one opportunity. You aim when you launch, and that's it. The spacecraft flies through space for 21 years and either hits the target or misses. If you miss, that's it. Mission failed. 25 years wasted. Even if you hit the target, even if you fly past Proxima Centauri at the right distance, you're moving so fast that you only have a brief window to collect data. At 60,000 kilometers per second, you cross the orbit of Earth, a span of about 300 million kilometers in less than 90 minutes. You zip through the habitable zone of Proxima Centauri, the region where liquid water could exist, in seconds or at most a few minutes. You need to take all your pictures, make all your measurements, collect all your data in that incredibly brief window. Then you continue on into interstellar space forever, never to return, drifting through the void between stars for eternity. So while breakthrough starshot is an interesting concept, based on real physics rather than science fiction, it remains highly speculative. the technology doesn't exist. The engineering challenges might be impossible to overcome, and even if everything works perfectly, it's still over 2 decades before you get any results. That's a long time to wait. That's a significant fraction of a human lifespan. And this is just to reach our nearest stellar neighbor. The next nearest star, Barnard's star, is about 6 light-years away. It's also a red dwarf, though slightly larger than Proxima Centauri. Sirius, the brightest star in our night sky, is 8.6 light-years away. When you look at Sirius tonight, you're seeing light that left that star 8.6 years ago. You're seeing Sirius as it was when you were 8.6 years younger. If you're 30 years old, you're seeing Sirius as it was when you were about 21, just finishing university or starting your career. If you're 50, you're seeing it as it was when you were in your early 40s. The Sirius you see tonight is not the Sirius of now. It's the Sirius of the past. Sirius is actually a binary star system. Sirius A is a white main sequence star about twice the mass of the Sun and 25 times more luminous. It's why Sirius appears so bright in our sky. It's relatively close and intrinsically quite luminous. Sirius B is a white dwarf, a dense stellar remnant about the size of Earth but with the mass of the Sun. It's the collapsed core of a star that exhausted its fuel and shed its outer layers. Sirius B is so dense that a teaspoon of its material would weigh about 5 tons on Earth. The 2 stars orbit each other every 50 years. Right now, in 2025, they're near their maximum separation of about 11 astronomical units, similar to the distance from the Sun to Saturn. They'll gradually come closer together, reaching a minimum separation of about 8 astronomical units, around 250. Vega, another bright star, is about 25 light-years away. If you're 25 years old and you look at Vega tonight, you're seeing light that left that star the year you were born. When that light began its journey toward Earth, you hadn't been born yet. You didn't exist. Your parents might have been looking up at that same star, seeing light that left Vega 25 years before that, 50 years ago total. The Vega you see tonight is a younger Vega, a Vega from the past, showing you what that star looked like a quarter century ago. Betelgeuse, the red supergiant in the constellation Orion, is about 550 light-years away. It's one of the most famous stars in the night sky. Even people who don't know much about astronomy recognize Orion, the hunter, with his belt of 3 bright stars and Betelgeuse marking his shoulder. Betelgeuse is easily visible as the bright reddish-orange star. On winter evenings in the northern hemisphere, Orion dominates the southern sky, and Betelgeuse is one of its most distinctive features. The light you see from Betelgeuse tonight started its journey toward Earth around the year 1474. That's during the Italian Renaissance, a time of incredible artistic and intellectual flowering in Europe. Leonardo da Vinci was 22 years old in 1474, already an accomplished artist, but years away from painting the Mona Lisa or the Last Supper. Michelangelo had just been born in March 1475, an infant with no idea he would become one of history's greatest sculptors. And light was leaving Betelgeuse, beginning its journey toward Earth. That light traveled for over 500 years, through the completion of the Renaissance, through the Reformation, through the Age of Exploration, through the Scientific Revolution, through the Enlightenment, through the Industrial Revolution, through 2 world wars, through the Space Age, through the Digital Revolution. And it arrived tonight, entering your eye, showing you Betelgeuse as it was in 1474. Betelgeuse is fascinating because it's a massive star nearing the end of its life. It's about 10 to 20 times the mass of the Sun and about 700 to 900 times the Sun's diameter. If you placed Betelgeuse where the Sun is, it would extend past the orbit of Mars. Earth would be deep inside the star, vaporized instantly. Betelgeuse has already burned through most of its fuel. It's in the late stages of stellar evolution, fusing heavier and heavier elements in its core. First hydrogen into helium, then helium into carbon and oxygen, then carbon into neon and magnesium, building up layers of different elements like an onion. Eventually, it will create iron in its core. And when that happens, the end comes quickly. Iron fusion doesn't release energy, it absorbs energy. The core will collapse in less than a second. The collapse will trigger a violent supernova explosion. When Betelgeuse explodes, and it will explode at some point, it will become incredibly bright. Estimates suggest it could reach an apparent magnitude of about -12, similar to the full moon. It would be visible during the day. It would cast shadows at night. It would be a spectacular sight, one of the most dramatic astronomical events visible from Earth in human history. The supernova would fade over weeks or months, but for a time, Betelgeuse would dominate the night sky. But here's the unsettling thing. Betelgeuse might have already exploded. The explosion might have happened centuries ago, perhaps in the 1700s or 1800s. We wouldn't know yet. We wouldn't have any way of knowing. The light from that explosion would still be traveling toward us, still crossing the 550 light-years of space between Betelgeuse and Earth. If Betelgeuse exploded in the year 1700, we won't see it until the year 2250, still over 200 years in the future. The star could already be gone right now. It could have been destroyed in a catastrophic explosion 200 years ago, and we'd still see it shining peacefully in Orion, completely unaware that we're seeing a ghost, an image of something that no longer exists. Reality and our perception of reality would be centuries out of sync. This is one of the most profound implications of light years. We never see distant objects as they are now. We always see them as they were. The farther away something is, the farther back in time we're looking. Distance equals time delay, and for very distant objects, that time delay can be enormous. Polaris, the North Star, is about 445 light-years away. When its light that we see tonight began traveling toward us, the first permanent English colonies in North America hadn't been established yet. William Shakespeare was just beginning his career as a playwright in 1580. He'd written some of his early works, perhaps The Two Gentlemen of Verona and Titus Andronicus, but most of his great plays were still ahead of him. Romeo and Juliet would come around 1595, Hamlet around 1600, Macbeth around 1606, King Lear around 1606. The greatest writer in the English language was just getting started. Within about 20 light-years of Earth, there are approximately 130 known star systems. This is based on data from surveys like the Gaia mission, which has precisely measured the distances and properties of over 1 billion stars. Some of these nearby systems are single stars like our Sun, alone with perhaps planets but no stellar companions. Others are binary systems with 2 stars orbiting each other, locked in a gravitational dance that may last for billions of years. Still, others are triple systems like Alpha Centauri, or even more complex multiple star systems. Now let's zoom out. Our Sun is part of a much larger structure, the Milky Way galaxy, a barred spiral galaxy containing between 100 billion and 400 billion stars, 26,000 light-years to the galactic center. The light we would see from the center of our galaxy, if we could see through all the dust blocking the view, left the galactic center 26,000 years ago. That's the Upper Paleolithic, the Late Stone Age. Humans were hunter-gatherers living in small bands. We were using sophisticated stone tools, creating elaborate cave paintings, making carved figurines, but we had no agriculture, no permanent settlements, no cities, no writing. The Milky Way is roughly 100,000 light-years across from one edge of the spiral arms to the other. If you could somehow travel at the speed of light, which you can't because nothing with mass can reach light speed, it would take you 100,000 years to cross the galaxy from one side to the other. 100,000 years of constant travel at the fastest speed possible in the universe. Modern humans, Homo sapiens, are about 300,000 years old as a species. We first appeared in Africa around 300,000 years ago, perhaps a bit earlier. You could have started crossing the galaxy when the first modern humans appeared, traveled at the speed of light for 100,000 years, covering 1/3 of the galaxy's width, and you'd still have 200,000 more years of travel ahead of you. You'd still be deep within the galaxy, nowhere near the far edge. Our sun orbits the galactic center at a speed of about 230 kilometers per second. That's about 828,000 kilometers per hour, over 800,000 kilometers per hour, fast enough to cross the United States from coast to coast in about 3 minutes. Fast enough to circle Earth's equator in less than 3 minutes. It's an incredible speed by any human standard. But even at this incredible speed, it takes the sun about 225 million to 250 million years to complete one orbit around the galaxy. This period is called a galactic year or cosmic year. It's the time it takes for our sun to make one complete circuit around the Milky Way's center. The last time the sun was in its current position in the galaxy, dinosaurs were just beginning to evolve on Earth. The first dinosaurs appeared about 230 million years ago during the Triassic period. These were small, bipedal creatures, quite different from the giants that would later dominate the planet. Dinosaurs like Herrerasaurus and Eoraptor were among the earliest, measuring just a few meters long, and the sun has only just now returned to approximately the same position in the galaxy where it was when dinosaurs first walked the Earth. All of that history, all of those changes, all of that evolution and extinction and transformation happened in one galactic year. Now let's leave our galaxy. Let's look at the nearest large spiral galaxy to us, Andromeda. Also called Messier 31 or M31, Andromeda is visible to the naked eye from dark locations as a faint, elongated smudge in the constellation Andromeda. It's one of the most distant objects visible without a telescope. On a moonless night far from city lights, you can see it as a dim, fuzzy patch. Ancient astronomers knew about it. Andromeda is larger than the Milky Way. It contains about 1 trillion stars, more than twice what the Milky Way has. Some estimates put it even higher. It's about 220,000 light-years across, more than twice the Milky Way's diameter. It's a massive, impressive spiral galaxy, one of the largest in our local region of space. And it's about 2.5 million light-years away from us. 2.5 million light-years. Let that sink in for a moment. The light we see from Andromeda tonight left that galaxy 2.5 million years ago. 2.5 million years. Try to comprehend that time span. 2.5 million years ago, Earth was in the Pliocene epoch, transitioning into the Pleistocene. The climate was warmer than today. There were no large ice sheets on Greenland or Antarctica yet. Sea levels were higher. Forests extended farther north than they do now. The genus Homo had only recently evolved. Homo habilis, one of our early ancestors, lived in Africa. Modern humans, Homo sapiens, wouldn't appear for another 2 million years. We were still millions of years and several species away from existing. Homo erectus wouldn't appear until about 2 million years ago. Homo heidelbergensis, a possible ancestor of both Neanderthals and modern humans, wouldn't appear until about 700,000 years ago. Neanderthals wouldn't appear until about 400,000 years ago. Homo sapiens, us, wouldn't appear until about 300,000 years ago. That's when the light we're seeing from Andromeda began its journey. It traveled for 2.5 million years, through the evolution of multiple human species, through the entire evolution of modern humans from pre-human ancestors, through multiple ice ages, through the spread of humans out of Africa and across the globe, through the invention of language, art, music, and storytelling, through the development of agriculture 10,000 to 12,000 years ago, through the rise of civilization, the invention of writing, the building of cities and empires, through ancient Sumer, Egypt, Babylon, Assyria, Persia, Greece, Rome, through the rise of Christianity, Islam, and Buddhism, through the Middle Ages, the Renaissance, the Age of Exploration, the Industrial Revolution, through 2 world wars, through the space age, through the invention of computers and the internet, through every moment of human history, and it arrived tonight. That ancient light is entering our telescopes and cameras right now, showing us Andromeda as it was when our ancestors were primitive hominids, barely distinguishable from apes, using the simplest stone tools with brains half the size of ours. Andromeda is also moving toward us. The Milky Way and Andromeda are approaching each other at about 110 kilometers per second. In about 4.5 billion years, they'll collide. Or rather, they'll merge. When galaxies collide, actual collisions between stars are incredibly rare because stars are so far apart. The vast majority of stars in both galaxies will pass by each other without any direct collision, but the gravitational interactions will be dramatic. The galaxies will pass through each other, their spiral structures disrupted and destroyed. They'll pull back together, pass through each other again, and eventually settle into a single large elliptical galaxy. Computer simulations show this process taking several billion years. Some astronomers have nicknamed this future-merged galaxy Milkomeda, or Milkdromeda. By the time this merger is complete, the Sun will be near the end of its life. The Sun is about 4.6 billion years old now, and has about 5 billion years of stable life left. In about 5 billion years, it will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around the core. This will cause it to expand into a red giant, growing to about 100 times its current radius. It will engulf Mercury and Venus. Earth might survive on the outer edge of the Sun's expanded atmosphere, but it will be a scorched, lifeless rock. So the Andromeda-Milky Way merger will happen around the same time the Sun is dying. If humans still exist then, if we've survived for billions of years, and perhaps spread to other star systems, we'll witness one of the most spectacular events possible: 2 galaxies merging. The night sky will be transformed. Instead of a faint smudge, Andromeda will grow larger and brighter over millions of years until it dominates the sky. Eventually, the 2 galaxies will interpenetrate, filling the sky with stars and glowing gas clouds. It will be beautiful and terrifying. But that's billions of years in the future. For now, Andromeda sits 2.5 million light-years away, a faint, fuzzy patch visible only from dark skies, showing us its past from the dawn of humanity. Beyond Andromeda, the galaxies spread out in all directions. Within about 10 million light-years of us, there are about 50 known galaxies forming what astronomers call the local group. Most are dwarf galaxies, small collections of a few 100 million to a few billion stars. The Large Magellanic Cloud contains about 10 billion stars. The Small Magellanic Cloud has about a few billion. These are irregular galaxies, satellites of the Milky Way, visible from the southern hemisphere as cloudy patches. Indigenous peoples in the southern hemisphere have known about them for thousands of years, incorporating them into their mythologies. The Triangulum Galaxy, M33, is the 3rd largest member of the local group after Andromeda and the Milky Way. It's about 3 million light-years away and contains about 40 billion stars. It might actually be a satellite of Andromeda rather than an independent member of the group. The local group spans about 10 million light-years. That's already an incomprehensibly vast distance. 10 million light-years means light takes 10 million years to cross it. When light left the far side of the local group, primates hadn't evolved yet. Mammals were still relatively primitive. Dinosaurs had been extinct for about 56 million years, but mammals hadn't yet diversified into all the forms we see today. And the local group is just a small structure in a much larger cosmos. Now let's talk about what all this actually means. Because a light year isn't just an abstract unit. It's not just a number astronomers use because it's convenient. It has real, profound implications for humanity, for our future, and for our understanding of our place in the universe. First, let's address communication. Because the light year creates fundamental, insurmountable barriers to communication across cosmic distances, and these barriers have implications that most people never consider. Radio waves travel at the speed of light. When we send radio signals into space, when we broadcast television shows, or make phone calls or send data, those signals propagate outward at 300,000 kilometers per second. That's the fastest possible speed. Nothing can go faster. But even at this incredible speed, the fastest speed allowed by the laws of physics, communication across light years takes years. Imagine we somehow established a colony on a planet orbiting Proxima Centauri, 4.24 light years away. Perhaps we solved all the technical challenges. Perhaps we built generation ships, or developed suspended animation, or found some way to make the journey. The colony is established. People are living there, farming, building settlements, creating a new branch of human civilization on an alien world. Now, imagine you're on Earth. You want to ask the colony how things are going. You send a message. How are the crops? Is everyone healthy? Do you need any supplies or assistance? That message travels at light speed for 4.24 years. 4 years, 2 months, and about 29 days. Your message covers 40 trillion kilometers at 300,000 kilometers per second, racing through the void between stars. Finally, after 4.24 years, it arrives at the colony. If they respond immediately, if someone sits down the moment your message arrives and composes a response and sends it back, that response takes another 4.24 years to reach you. Another 4 years, 2 months, and 29 days of travel time. You receive their answer 8 years, 5 months, and about 2 months after you sent your question. Over 8 years for a single exchange. Think about what happens in 8 years. Children grow from toddlers to preteens. Careers change. Relationships begin and end. Political administrations change multiple times. Technology advances. The world transforms. And you're waiting the entire time for an answer to a simple question. You asked about crops. By the time you get the answer, those crops were harvested, eaten, and forgotten 4 years ago. You asked about someone's health. They might have recovered or died years before you hear the news. You offered to send supplies. By the time they receive your offer and respond, their situation has completely changed. Maybe the crisis has passed. Maybe it got worse. Maybe they solved it themselves. Maybe they didn't. Any kind of real-time communication, the kind of immediate back-and-forth conversation we take for granted on Earth, is completely impossible across these distances. Imagine trying to have a conversation with 8-year delays between each exchange. You say something, 8 years later, they respond. You respond to their response. 8 years later, they get it. A conversation that would take 5 minutes on Earth would take decades across interstellar distances. Debates would span lifetimes. Political negotiations would take centuries. Someone could propose a treaty, and the response wouldn't come for decades. By the time the response arrived, everyone involved in the original proposal would be dead or retired. Their grandchildren would be continuing the negotiation. This has profound implications for governance. A colony 4.24 light years away couldn't be governed from Earth in any meaningful sense. Any laws passed on Earth, any directives sent to the colony would arrive over 4 years out of date. The situation on Earth could change completely between when a message was sent and when it arrived. A new government might take power. New policies might be enacted. The old directives might be obsolete by the time they arrive. The colony would need to be autonomous, completely self-governing, capable of making its own decisions on everything from resource allocation to conflict resolution to emergency response to scientific research to social policy. Because waiting over 8 years for guidance on every decision would be impossible. Life can't wait 8 years. Emergencies can't wait 8 years. Decisions need to be made in real time. And over generations, the colony and Earth would drift apart culturally. They'd develop different customs, different values, different ways of solving problems. They'd be shaped by their different environments, their different challenges, their different experiences. Earth culture would continue evolving in one direction. Colony culture would evolve in another direction. They'd share a common origin, a common history up to the point of separation, but from that point forward, they'd diverge. They'd still exchange messages. They'd still communicate, but it would be more like archaeological correspondence than a living relationship. Each message would be a snapshot of a moment in time from years ago. By the time you read about events on the colony, those events would be ancient history to the colonists. They'd be reading about your world as it was years ago while living in their present. For settlements at greater distances, the isolation becomes even more extreme. A colony 10 light years away would have a 20-year round-trip communication time. You could send a message to your children living there, and their response would return when your grandchildren are adults. You might be dead before you hear back. The conversation would span generations. A civilization 100 light years away would have a 200-year communication delay. You send a message, and neither you nor your children nor your grandchildren nor your great-grandchildren would live to see the reply. Only your great-great-great-grandchildren, living in a world utterly transformed from the one you knew, might hear back, and the civilization responding would be responding to a message from their own distant past, from ancestors they know only through history. This brings us to the Fermi paradox, one of the greatest mysteries in science. The paradox is simple to state, but deeply troubling in its implications. The universe is vast. There are hundreds of billions of stars in our galaxy alone. Many of these stars have planets. Some of those planets should be capable of supporting life. Even if life is rare, even if intelligent life is extremely rare, there should still be many technological civilizations out there somewhere. Some should be millions or billions of years older than us. They've had time to develop advanced technology, to spread across their region of space, to send out signals, to make their presence known. So where are they? Why haven't we detected any signs of alien civilizations? We've been listening to the stars for decades with radio telescopes. We've searched for signals, for patterns, for anything artificial. Nothing. Silence. The universe appears to be empty of intelligence except for us. This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked over lunch in 1950, "Where is everybody?" There are many proposed solutions. Maybe life is rarer than we think. Maybe the jump from chemistry to biology is extremely difficult. Maybe complex life rarely develops. Maybe intelligence rarely evolves. Maybe technological civilizations destroy themselves shortly after developing advanced technology, wiping themselves out before they can colonize space or send out lasting signals. Maybe civilizations exist but are staying quiet intentionally. Maybe they've learned through bitter experience that broadcasting your presence is dangerous. Maybe the universe is a dark forest where everyone hides because announcing your location invites destruction. Maybe advanced civilizations deliberately avoid contact with younger species like us, waiting for us to reach some threshold of development before revealing themselves. Maybe they exist but communicate in ways we can't detect. We're listening for radio signals because that's what we use. But maybe advanced civilizations use quantum communications, or neutrino beams, or gravitational waves, or something we haven't even discovered yet. We're listening for smoke signals while they're using fiber optics. But here's another possibility, perhaps the most sobering one. Maybe space is simply too big. Maybe the light-year distances between stars are so vast that contact is effectively impossible, even if civilizations are common. The average distance between technological civilizations in our galaxy might be thousands of light years. If civilizations are rare enough, if there are perhaps only thousands of them in a galaxy of hundreds of billions of stars, they'd be scattered so far apart that they'd never encounter each other. Radio signals would spread out and weaken over those distances, becoming indistinguishable from background noise. Even if you could detect a signal, what would be the point? Any message sent would take thousands of years to arrive. Any response would take thousands more years to return. The civilization that sent the original message might be extinct by the time you reply. The galaxy might be filled with civilizations that will never make contact because the distances are too great. Each civilization develops alone, asks its questions alone, makes its discoveries alone, looks up at the stars and wonders if anyone else is out there, and eventually dies alone without ever knowing the answer. The light year stands as an impenetrable barrier that even advanced technology might not overcome. This isolation is profound. Even if we're not alone, even if the universe is teeming with intelligent life, we might be effectively alone because we can never reach them. The distances measured in light years separate us as surely as if they didn't exist at all. But there's another side to this isolation. It makes Earth precious beyond measure. If we're truly alone, or if we're so isolated that it doesn't matter whether other civilizations exist, then Earth becomes infinitely valuable. It's not just our home, it's possibly the only home for hundreds or thousands of light years. Carl Sagan spoke beautifully about this when reflecting on the pale blue dot photograph. In February 1990, Voyager 1 was about 6 billion kilometers from Earth, beyond Neptune, heading out of the solar system. Scientists commanded it to turn its camera back toward Earth and take one last photograph. Earth appeared as a tiny pale blue dot, less than a pixel in size, suspended in a beam of sunlight. Sagan wrote, "Look again at that dot. That's here. That's home. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam." He continued, "Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. That pale blue dot sits in a galaxy 100,000 light years across, in a universe 93 billion light years wide. Earth is incomprehensibly tiny compared to the cosmos. And yet, as far as we know, it's the only place where life exists, the only place where consciousness has arisen, the only place where beings can look up at the night sky and understand what they're seeing. Understanding light years forces us to confront difficult truths. The distances are so vast they might be insurmountable. We might be confined to Earth, or at best to our solar system, for the entire future of our species. The stars might be beautiful lights in the sky, but forever out of reach. But perhaps that's okay. Perhaps being small and isolated in a vast cosmos isn't a tragedy. Perhaps it's what makes us precious. It means we matter. It means what happens here is important. It means we need to take care of this small world because it might be all we ever have. The light year isn't just a unit of measurement. It's a reminder of scale, of vastness, of barriers, of our smallness and isolation, but also of our uniqueness and value. Because in all those light years, across all those vast distances, Earth is the only place we know where life exists, where consciousness arose, where beings like us can understand the cosmos. When you look up at the night sky tonight, remember what you've learned. Those stars are light years away. That band of light stretching across the darkness, the Milky Way, spans 100,000 light years. Andromeda, visible as a faint smudge in dark skies, is 2.5 million light years distant. You're seeing ancient light, photons that have been traveling through space for years, centuries, millennia, millions of years to reach your eyes. You're connected to those distant stars and galaxies across the vast distances of space and time, linked by light that has crossed the cosmic void to reach you. The light year is the scale that breaks our brains, 9.46 trillion kilometers, a distance so vast that counting to it would take longer than human civilization has existed, a distance so incomprehensible that no analogy fully captures it, a barrier so formidable that it might forever limit how far humanity can reach into the cosmos. But it's also the tool that lets us measure the universe, that lets us understand, at least intellectually, the true vastness of creation, that lets us map the cosmos and determine our place within it. Thank you for joining me on this journey through the incomprehensible scales of the universe. If you found this exploration valuable, please consider liking this video and subscribing to the channel. Your support helps me continue making these deep dives into the wonders of space and our place in it. And remember, the next time someone mentions light years, you'll know what they really mean. Not just a big number, not just a unit of measurement, but a distance so vast it challenges everything we know about scale, a distance that connects space and time, a distance that might define the limits of human reach, and a distance that reveals our profound isolation and precious uniqueness in an almost incomprehensibly vast universe. The light year, the scale that breaks our brains, and the tool that lets us understand the cosmos. Good night, and may you never look at the stars the same way again.